Okay, so the idea now is to talk about why every quadratic form can be brought into a diagonal form if you want sum of squares. So we start with the quadratic form above R or C this way, Qx equal x transpose Ax. Now, the key idea is that for quadratic form, the representing matrix is A, which is symmetric over the reals, or Hermitian over the complex numbers. Now, for every symmetric or Hermitian matrix, we know that it is unitary or orthogonal in the real case, diagonalized. So you know that you can find an invertible matrix by the spectral theorem such that P transpose AP equals D. So you can diagonal the matrix that represents the quadratic form. Now, when you get to a matrix that is in diagonal form, you found how the quadratic form is represented by a sum of squares. So you know that you must have this matrix that you need in order to transverse the quadratic form into a diagonal form, namely sum of squares. Again, this is because the representing matrix is symmetric, which can be diagonalized. Now, this invertible matrix that you diagonal with is what is used to take a quadratic form into its sum of squares. On the columns of P, there is the base in which the quadratic form is represented in sum of squares. For example, maybe I'll give you an example. So let's see an example. Example would be of this quadratic form, and we will see how we take it and translate it into the diagonal form. So you can see here how the thinking goes, but he will look for the eigenvalues, and the eigenvalues will tell it what is the diagonal form. So you can see it right over here. It takes from this quadratic form the represented matrix because the coefficient of x squared is 3, the coefficient of xy is 4, so you divide it by 2 here and 2 here, and for y squared is -1, so you put it right over here. You can see that this is a symmetric matrix. Now, in order to find its symmetric matrix, so it must be orthogonal diagonalized. It can be orthogonal diagonalized. So you can see that it finds the eigenvalues, and now the eigenvectors will create the diagonalizing matrix. And because for orthogonal matrices you know that the transpose equals the inverse, so similarity, to find the similarity, that what I do now is the same as finding conjugariance, so it's the same. So you can see how he found using the eigenvalues the base in which the quadratic form is as sum of squares, and it just gave some variables to what he found in order to be in a very neat way. Okay, so this is it. This is the idea of why you can transform each quadratic form into its diagonal form, or if you want sum of squares. Thank you all, and that's it.